Hey guys, welcome back to another video. In this one, we're going to be doing the maximum minimum sums of at most size k subsequences. So in this one, you're given nums and k. Return the sum of the maximum and minimum of all subsequences. Subsequence is basically not contiguous; it's deleting elements. Okay. With at most k elements, this number is very large. Do this. Okay, so here if k is 2, so for example, like 1, 2 is a subarray and so on. Okay, so they show you all these. So 1, okay. They show you the mins and the max and add it together. Here, one number, so it's just 5, 0, and 6. So it would be like the 5 is the min and the max and 5, so it'd be like 5 times 2, 0 times 2, 6 times 2, which is 22. Here, k is 2. Okay, so let's write some notes. So for one thing, subsequences don't have to be unique. But it looks like the order doesn't matter. Because like in 111, for example, you can pick like, the first one and the second one, or the first and the third one, or the second and the third. But like you can't do this as well, and like, right? So that's why there's only 3. Okay. For all of them, okay. Okay, so there's 10 to the 5th nums. K is very small, 70. So you can do like n times k squared. Would be close, I guess, but n times k would work. Okay. Okay, so if they were contiguous, you could basically just run a sliding window through all k, and that would be n times k. Yeah. Because they're not contiguous, we can't get like all subsequences, but what we can do is we can figure out like for a given k, right? Like let's say our numbers are like 1, 2, 3, 4, 5. And let's say k is like 3 or something. Like if we say we can predefine a minimax, like we could say like this is the min. So how many times is this the min in a subsequence of 3? So basically we have to pick this number, and then we have to pick 2 more out of here. So it's like 3 choose 2, which is just I forgot, like NCR or whatever that thing is. So that's just n over n minus k, or this is like n factorial. I'm gonna send this k factorial. So in this case, that would be, so n is 3. We choose 2, so that would be like 3 over 2. No, it'd be 3 factorial, so it'd be like 6 over, let's see, 1 times 3. So it's like 2, I think. So let's see if that's right. I feel like it's not. Wait, did I do the math? Let's say 3, choose 2, right? So 3 factorial, which is 6. This is 1, and this is 3. So I think that's right. So let's see. So we could pick like 3 and 4. Yeah, definitely not, right? So, or we could pick 4 and 5, or we pick 3 and 5. So we should get 3. So what did I screw up? So if we have these 2 that we can, or these 3 that we can pick, but we're gonna pick 2. Okay, so it's 3 factorial, 6. Oh, wait. Oh, so 3, wait, no, 3 factorial is, yeah, I think. How am I getting this wrong? I don't understand. Oh, it's because k is 3 here. This is not 3, this is 2. No, this is 3. Oh, this is 3, but we can only actually choose 2. So that's what we did wrong. So we have 3, we can only choose 2 though. So 3 minus 2 is 1, but this is 2 factorial, which is 2. Okay, there we go. It's like, what did I? Okay, so this is correct now. So basically, given a number and how many we have left, we can calculate how many times it's the min or max with and choose k. And we can do this for every single k, right? So like we could say like, okay, for this number, for a k of 1 through 70, let's calculate this. And n choose k. So factorial obviously is a long time, but you can pre-compute factorials. So we can pre-compute. So basically, if I need like some number 1 to n factorial over some number 1 to n factorial. So inverse factorial with a mod, you need to pre-compute. This you need to pre-compute as well. And you don't just do a straight divide. You have to do like the Fermat's little theorem thing. for inverse factorial, because basically like when you do division with a mod, you can't just divide directly. You need like something else. So yeah. And so we need to write a function to calculate. Basically, it's like to do 1 over n factorial is n factorial to the some big prime number. So that's the 10 to the 9 plus 7. So we could use this like mod value. Minus 2. And then you just mod the whole thing by the prime number. And this is 1 over n factorial. And then from 1 over n factorial, we can get the rest. So we can just say like, well, if we have like 1 over n factorial, which we can get in log n time, we can do it in n time as well, technically, if we want to. Yeah, but we're not going to. Okay, yeah, because 10 to the 9 is a really big number. So so this would be like linear to 10 to the 9, which wouldn't work. So from here, we can get this, like for example, 1 over n minus 1 factorial by doing, so this is basically just 1 over n factorial times n, because that would be n over n factorial, which then is canceled, and then you have n minus 1 factorial, which is this. So once we get like the big number, we can get the rest. So we have to write a function to calculate a fast power, because yeah, like if I do like 2 to the million, I don't want to do just 2 times 2 times 2 times 2 times 2. What I really want to do is like 2 to the mil. I want to do like 2 to the half mil. And then I basically want to square that, and that would give us the whole thing. So we can essentially think about it. You have a tree, you just like do one half at a time, and then that gives you a log power. So let's write that first. So let's write func like fast pow. In Python, this is already provided. In other languages, it's not. I think in C++ maybe provided too. So we have basically a number. We have a power. Yeah, we have a power. And then from here, we're just going to mod it by mod, like automatically. So we'll just do, or I guess we could provide as well. So typically it looks like this in the fast power function. So we'll just do it this. So basically what we got to do is if the power is, I haven't done this in a while. You can do it recursively too, but it's not as good. So if the power is 0 or 1, if the power is 0, we want to return 1. So we can start with that. So if power equals 0, return 1. And then from there, I think you can do everything else, I believe. So basically, let's just think of a number. So if we have like 6, so you need binary for the number. So let's just say like 1s and 0s. The way this works is, trying to remember. So the power keeps growing, right? So this power will be represented in binary, but basically this is like 1, this is 3, this is so on. So I think what you do is you just keep squaring the power. No, you keep squaring the base. Yeah, you keep squaring the base. So like 6 to the 1 is this, but if we want 6 squared, it'll be like this, right? So it would be like 6 times 6. And then this will be like 6 to the 4th and 6 to the 8th and so on. So you keep squaring the base and you have a result. And actually, yeah, I think this can handle everything. So we have a result. You keep squaring the base. So base. And while the power is non-zero, we basically just keep squaring the base. And anytime we have a 1, we multiply our result by our base, and that's the answer. So in this case, for example, our base would start off at 6. We'd say like, oh, there's a 1, so then our result is 6. So we shift left. Now our base is 36. This isn't there, so we do this again. And it's 36 times 36. Yeah, and so on. Because this is like 2 to the 4, 2 to the 8, and to go from like 2 to the 4 to 2 to the 8, you basically square, right? So I think that's how you do it. We'll double check later, but I think this is right. So while pow greater than 0. So if the pow and 1, or mod 2, whatever you want, so if this is true, Then we do result equals result times the base modded by mod, so we don't get overflow. Then we square the base. And we can check this later if it's correct, but basically, yeah. And then we also shift the power. I think in every language it's the same pretty much. Shift the power to the right one. And finally, we return the result. So this is like fast power, not recursively. You could also obviously do recursive. You could take your power and just like divide by 2. So if you have like 2 to the 5th, you say like, let me do half of that. And then the base case would be like 1 and 0 and so on. So that works too. So this would also this would handle 2 to the 0 because this would just be 1. So it kind of handles everything. Okay. So now what we need to do is we need to compute factorials from 1 to n. So let's do that next. So we can say let mod equals 10 to the 9 plus 7. Okay. So yeah, we want to compute factorials from basically 0 to n. Sure. I mean, we might not need so many. We can technically do it to 0 to k. It's probably a lot better actually thinking about it because it's way smaller. Yeah, because like if you have a number, you can only pick. Actually, no, it's n choose k, right? So no, we definitely want n. Yeah, it's n choose k, so we need n. Okay, so so that's fine. So we can just say like bar factorials, facts or something, equals array repeating. So the first number will be 1, count will be, just go to like n. So we'll say like n, let's count. Yeah, so this will be n. Okay. Now we basically just want to get these factorials. So for I and this is pretty simple while loop for factorials. So this is like facts count. So basically, like if you think about it, so this is factorial of 0 and then 1 and so on up to n minus 1. And the factorial is just the next number plus the current number. So this is just facts I equals facts I minus 1 times I mod because we want to not overflow. Okay. Now we need inverse factorials, so we kind of need the same thing. Facts equals array repeating whatever we want. Okay, so we need to calculate inverse factorial first. So facts of n minus 1 equals, so this is basically 1, or this is like n minus 1 factorial. So this is fast pow. Number is n minus 1. That's how many that's like the base. The power is mod minus 2, and this is mod. So now we have that. Now we need the rest. So for I in stride from, so this is n minus 2 through 0 by -1. Okay. Oops. Okay. So now this is facts I equals the old one. So facts, or this is actually not facts. This is, yeah, we need inverse. So inverse facts, inverse of I plus 1. So if so this is like for example, if we're at 1 over n minus 2 factorial, it's the previous one times, right? Like if our number is this 1 factorial, how do we get it to n minus 2? Well, it's just n minus 1 times this whole thing. So that's just times I plus 1. So this would start off as like n minus 2, and we'd get this mod. Okay. So now we have factorials and inverses. Now we need a result. Now we also need a combinations thing, and I'm going to write that in here because we're going to use these things. So we can just say func com. So com takes n and k. So n int k int. And this is what I said. So basically return n factorial, which is facts of n, times, so that's why we can't do divide, so we have to do the inverse factorial. So inverse n minus k factorial, or go like this, n minus k, times inverse of k. So these are basically inverses. Okay, and we want to return it int here. And we want to return it int here. And we want to not overflow. So that. Okay, hopefully this doesn't overflow. And now we can do everything. So we have to go through all the numbers and say, like, if this is the min, how many can we pick from? And for every single k as well. So for I in 0, and this is basically n less than n. Okay, and for k, so for j in, so k can be at least 1 up to k, right? Most k, so for j in 1 up to k. Okay. All right, so first of all, we have to determine if we have enough numbers. So let's determine how many numbers we have, like for the min and the max. So int, like the min means, so this is basically like how many numbers are there before this. So that's I minus, or is it just I? Like if we're at index 0, there's nothing. Yeah, so I think this is just I. If we're at 1, there's 1. Yeah, so this is good. Max equals n minus something. So here, for example, n is 3. How many numbers are there after this? N minus I minus 1, I think. Okay. So we have to have enough numbers here. Actually, so this I, by the way, it shouldn't be from 0 to k. It should be from 0 to k minus 1, because we can't pick k. We have to pick k minus 1 numbers here. So this is actually just like 0 less than k. Okay, so this is how many numbers we need. So if min is less than, or we have to have enough numbers here. So this has to be at least j. Then we can get a calculation. So we can basically say, so this is just result equals result times, so we com. So the number we can pick from is min. The number we need is j. And that's how many times this thing appears. So there's actually plus. So this is how many times we can use the min, and then what's the actual like number. So like let num equals nums n or I. So this is like, this is the actual number we pick. So num. So basically this is how many times we can pick it. This is how much mod. Same for the other. If max is, so if this is the max, then this is how many other numbers we pick, and we need to have at least j we can pick from. Then we do the same thing. So is this right? Actually, min is how many we can pick. J, yeah, that's correct. Now here's max is how many we can pick, where like this is the max, so it has to be numbers below it. Whereas, yeah. Okay, and then we just return results and see how many errors we have. This is a pretty hard one, so I'd assume a lot. Int. Definitely think, I don't know if it's just LeetCode, but Swift debug logs suck. Count. Okay. Also don't know why, like, yeah, things don't turn red either, which is like pretty annoying. Misspelled. Pow mod. Oh, I didn't give it labels. Oh, it's because these need to be unnamed args. Mutating. Where? 17. Wait, what? Pow is a let constant. I guess it's in here. Okay, so. Okay. How about now? That would be pretty insane if it's all correct, to be honest. Yep. Okay, so we screwed something up. So if nums is 3, 10, and k is 1, it should be the number twice. So what would happen in this case? Let's use this case. So let's just walk through what would happen. Okay, so let's just say our factorials are all this is correct. Let's just go to this section. So n is 1, min is I, which is correct. Max is 1 minus 0, so these are both 0, the num. Let 0 to k, so it should be 0. If min is greater than or equal to j, so this is 0, this is 0, then we go here. So we definitely go here, and we can determine this. We definitely should be in these blocks. So that's, I don't think that's a problem, but let's just confirm. Just so we don't waste our time. So okay, so we got in those. Okay. Res plus com min j. Okay, so what would happen if com min j, so this is factorial of 0 times the inverse of n minus k. What's n minus k? Oh, this is like negative. Well, that's a problem. So actually, wait. K is 0. N is 0. No, so it'd be 0, 0, 0. So you should just give 1. So fact 0, inverse 0. Let's print the inverse. Probably have that wrong somehow. Okay, the inverse is 0. Oh, it should be 1. Yeah, it should be 1. Why is it 0? Probably screwed something up. Inverse equals, so this is like inverse factorial of 1 here. And then to get 0, it would be, yeah, basically just like 1 times I plus 1 mod. There's 0. Maybe my fast power screwed. Well, no, because the other ones are all correct. I guess let's think about what this would do. So num here is, like, we basically calculate this as the first one. So inverse n minus 1. Yeah, inverse n minus 1. So inverse of 0. Wait. Oh, do I need n plus 1 here? So inverse of 0 is this. Actually, yeah, this would just calculate this directly. So this would be inverse of 0, because there would be no n minus 2. So inverse of 0 is fast power of 0 to some number, mod. Okay. So the base would be, this would be 0. This would be some big number. So 0, or actually, wait, no, this wouldn't be, would it be 0 actually? Maybe that's incorrect. Let's see, let me go back. So n minus 1. Yeah, I guess what's 0 factorial? Is it 1? I think it is. So I think I need the edge case of, like, if it's 0, then it's 0. Yeah, let's see. So if I do, or if I just like type in 0 factorial, I guess. Because 0 factorial is 1. But we're basically, the problem is we are, oops, go away. We are doing 0 to some power, which is 0. So what we want to do is, we can hack this power. We can say if num is 0, return 1, I guess. Num equals 0, return 1, because that basically means, like, we want inverse factorial of 0, so this isn't really a power. Or we could do it somewhere else, but this is fine too. I think that'll handle it. interesting. We still get. Oh, we also need to sort our numbers. We forgot that completely because we need to know how many numbers are past this. So, okay, pray to God. Oh, okay. Sorted. Okay. How about now? Come on. Oh. 64. Okay, we still got something wrong apparently. Now it's gonna get pretty tough to debug, to be honest. Okay, so basically in this, 2 will be the max. 2 will be the max. So this is 3 choose 2. So this was like the thing I had before was like 3. And 2 is the min once. How do we even get 16? Yeah, 2 is the max 3 times, right? Yeah. That should be 6. And 2 is the min in only one array, which is just 2. Oh, I guess, we can have different lengths arrays, right? So actually 2 is the min here. 2 is also the min in 3 of these. So that's 8. And then in the 3 number, it's 3 choose 2. So that's where it's another 3. So that's 14. Is that right? So, oh yeah. So 2 is the min here. 2 is the min in 3 of these. So 8. 2 is also the min in, yeah, 2 of these. Or 3 of these. So it's 14. How did I get 64? And then 2 is also the min in this whole thing. Or actually, sorry, it's the max in all of these. Yeah, yeah. So it's only the min in one thing. It's only the min in this, but it's the max in this, max in 3 of these, 3 of these, so 6, like 7. Yes, it's 2 times 7 plus 2. Yeah, which is 16. How did I get 64? So I went like too far somehow. Why? I feel like this is just going to... Okay, so let's correct this first. So we can say like if n minus 1 equals 0, we'll just make it 1. Otherwise we'll calculate and then we'll do all of that stuff. Okay, so how do we get this wrong? That's a good question. So where do we call combinations? We call combinations here. So let's just print the min and the max and like see if we get, I guess, for all these different things. So print. So let's start there. Let's make sure like we're actually getting the right numbers. So in length 0, wait, why are we getting so many? For I to n, for 0k. Yeah, like why are we getting so many? That's a good question. Oh, okay, this is how many times like 0, for example. But 0 doesn't, we don't really care about 0. So let's just say, let's kind of hack this a little too. Let's say if yeah, let's hack this because basically we don't care about anything other than 2. So if num doesn't equal 2, let's just continue. And then let's see the ones with 2. Okay. So 330, 333. That's clearly not right. So this is k is 0. We can pick 0. We can pick... Wait. If we can pick 0, then what happens actually? Combination. So it's basically like 3 pick 0. So what would that equal actually? So that would be 3 factorial over... Yeah, okay, that doesn't work. So I think we need to say if j is 0. So actually what we need to do is we don't want j to be 0 ever. So we can do this. And we can also, like, in an array of 1, the element always works. So we can just add that ahead of time. So we can basically just say result equals result plus, like, our current number. Like, basically all these numbers by itself will always work, right? So we can just add that somewhere. Yeah, sure. So we can just add it here, for example. So we can say, like, result equals result plus num times 2, because it will always be the min and the max in itself, mod. So that will handle that. And now we can actually have some picks here, and hopefully that's corrected. Crap. Oh yeah, well, we have this thing. So let's see if that solves most of them. Okay, it solves all of them but the last one. Okay, so we still have the problem of this. So let's add that back in and let's see what happens now. Okay, so 3, 3. So that is correct. We have 3. And we're printing the min and the max. Oh, the max is 0. Wait, 3 can be the min. How can it be the min 3 times? It can't be the min 3 times. It can be the max 3 times. So I guess we screwed something up. So max is... Oh, okay. So I think this is reverse, actually. So this needs to be this. Because this is like the numbers in front of it. Or this is the number behind it, and this is this. Let's see if that solves it. So now the min, it can't be the min, but it can be the max 3 times and 3 times. That's 6. So what am I missing? So it can be the max. It can also be the max in this whole thing. Right? So this is what? K is... Yeah, so K can be 1. Or I guess, no, K can only be 1 and 2. Yeah, because if we pick this... Yeah, if we pick this, we can pick 1 more or 2 more. So if we pick 1 more, it can be 3. If we pick 2 more, it can be 3. It can also be by itself. So how is that even... Like, this is 1, this... Oh, yeah. We could pick 1 more. We could pick... Yeah, so it's 12 plus itself twice. Okay. So this is actually right. So it can be 3 and 3. Okay. Now, if min is greater than or equal to j, obviously not. So now we only do the max. So we can say, like, print, like, max, basically. Print, like, here or something. So this should get printed twice, and this should never get printed. It's kind of a pain. Wait, how are we getting there? Huh? I have this skip. Min and the max. Oh, this is the wrong one. Okay. There we go. So we only go into this block. That's what I thought. So we get 3 and j, combination of 3 and 3. Or 3 and... 3 choose 2. Yeah, so it's 3 choose 2 and 3 choose 1, which would both give us 3. Let's print that, I guess. So this... Okay. So we should get 3 twice. We got 12. Okay, so we're like overshooting by a lot. So it's the column that's wrong. So facts n. So this would be like 3 factorial. Let's print those as well, I guess. Print facts. And print inverse factorials. Let's just get rid of all these other does cases as well. And this is such a pain. This is where I would just ask the LLM, what stupid thing am I doing wrong? Did I get rid of these again? Oh, yeah. I think I got rid of the one I wanted. No, okay, this is good. Okay, so let's take a look what the factorials are. So 1, 1, 2, 6. What? 1, 2. Okay, so this is basically like 1 over 2 factorial. This is 1 over 1. So these are just incorrect. Yeah, so the inverse factorials are the thing that's screwed up. like this should be, or this should be inverse factorial. This should be 1. This should be 1. So how are we getting 2? No idea. So this would be like inverse factorial of 3, and then the other ones and so on. So inverse I plus 1 times I plus 1. Yeah, it makes sense to me. Okay, so what am I doing wrong? So unless the fast pow is wrong too, which it very well could be. So let's see. Oh, yeah, so this needs to be n minus 1 factorial, not, so that's what's wrong. So this would be facts n minus 1. Yeah, like I think I wrote earlier. Okay. Way too many places you can make mistakes here. Hopefully that's right now. Nice. Hopefully it's all correct. Praying to God. This is definitely one that, like, in a coding interview you would never get asked, in my opinion. And I'm kind of rusty doing the combination, so I screwed up. Oh, let's pray that we don't have any more bugs. It's also hard to debug because inverse factorial is like, it's not obvious like what it should be. Let's just submit. Come on. God damn it. How are there so many? I had another bug, I guess. Okay, so getting sick of this. All right, let's use this test case, get rid of this, and let's add the logs back in, I guess. And see, oh, wait. Oh, it's because I have this thing. Yeah, obviously. Okay. God damn it. K is 6. So I'm getting a overflow. Where? Solution 17? Here? Okay, so I was kind of worried about this, but I wasn't sure. So we could just say like let res equals, we can basically break this down into multiple things, like output equals this, mod, and then we can return the next part. Okay, still not used to overflow in Swift. Let's see if that fixed it. Okay, it did. Nice. All right. Now, come on, no more. Okay, thank God. Okay, so let's get rid of all this. Yeah, so I think in Swift, integers are base 64, but these can still be pretty big. So like this is basically roughly an overflow in int. So if you do like 10 to the 9 times 10 to the 9 times 10 to the 9, they can overflow. So okay, so now we have the time is nk. The space is n. Hopefully this was, maybe this is a little bit confusing for some people. You can write a recursive fast power, but the idea is you basically need a logarithmic, or you should know how to do a logarithmic power. Also, I'm quite shocked that this isn't just included in the standard library for, I mean, there's probably some import you can use, but for most languages, because like normal power sucks. So maybe there's like some optimizations. I don't know. And like power is pretty common, so yeah, I guess maybe that's why Python's better at this, because it has all these like built-ins. But I'm sure there's like if you didn't use LeetCode, there's imports you can use to have these things work. All right, so let's take a look at how we can improve this. So once again, I'm gonna just feed it. Let's leave the logic. I'm pretty happy with the logic, so let's just see what we can clean up. I mean, obviously you can clean it more. You can clean up more if there's production code. Definitely recommend that. You know, if you're like working, write a PR and then ask the LM to review it. Try to have as clean stuff as possible. Don't just have a bunch of slop, and don't have it AI generate everything for you, or at least have it AI generate and then go and fix yourself. Because yeah, okay. Oh, nice. Swifty. Let's take a look at how this gets improved. Okay, so this is the same. All right, let's take a look. So, okay, so they have a private variable, don't really care. Sure. Don't really care about that. Okay. Pre-compute. int64. So they use int64, but I don't think it matters. I mean, I think it's, yeah, I think it's just the same. Okay. So they do what I did here, same. So this is important, or like if n is 0 or something. Actually, let's see. So in factorial, okay, this is the same. Okay, so they just mod it. Okay, so they do one, then mod it, then do the third. That's the same. Looks kind of ugly, but this is the same that I did. So far, nothing better. If k equals greater than or equal to 1, for k in, oh, okay, so I see. So, I mean, this also doesn't really matter. I don't know why this is here. C add result. Yeah, I honestly don't see anything better. So I don't think anything's better. In fact, I think I honestly like my solution better. So this is a case where it was good to begin with, which is what you're kind of shooting for, you know. So yeah. But yeah, a lot of concepts here. Combinatorics, fast power. If you've never seen Fermat's Little theorem for inverse factorials, look it up. Maybe that's a little bit confusing. Used in a decent amount of problems. But yeah, the idea is you can't just divide numbers when you're using modular arithmetic. It doesn't work. Yeah. And you could think about how that breaks down really quickly, right? So if you have an inverse factorial, it like you're gonna get decimals and stuff if you just do straight divides, right? Like for example, if I do like 10 like mod 5, this works, but now if I do like, or 10 over 5, but if I do like 10 mod 3 over 5, now I get like a decimal. So it doesn't, you basically, the idea is you just do this, prevents you from having decimals. So yeah. And I don't remember the exact logic for all of it and like exactly how it works, but it does work. So, and not super confusing. Yeah, I think I'm gonna cut it here. So quite a long one. Definitely a reasonably hard problem. This is a good one if you've done a lot of LeetCode to just like maybe like honestly for me even like redo it, make sure you don't have mistakes. There's like a lot of tricky stuff here. So just a good, generally reasonably hard problem to do. So yeah, hopefully you liked it, and I'll keep making more. So thanks for watching.